Hi everyone, we are on 11.8 now. We actually skipped section 11.7, which is a summary of how all the different tests work. And so if you would like to just practice problems that are just different tests to work with, whether it's alternating test, alternating series test, or geometric series, or ratio test, or root test, or anything, they mix them all together and put them in one big section. That's what 11.7 is. So there's nothing really new for us to look at there. So we're going to jump into 11.8, which is power series. Now, a power series is a series, just like if you were testing any of the other series, except now, instead of just adding numbers together, we're actually going to work with adding functions together. So, for instance, up here on the top, this is a power series. And it could be written as, if you plug in 0 and 1 and 2 and 3, you would get these terms here all added together. You would get a polynomial, and actually an infinitely long polynomial. This one, the original one that I'm talking about at the top, that one would be centered at 0, but you could center a power series at any point. And so more generally, if you center it at a point A, that's just any number, then your series looks like this one down here on the bottom, or kind of in the middle here. The summation from n equals 0 to infinity of any constant multiplied by x minus a number, so you could be like x minus 1, x minus 2, raised to an n. That would give you a infinitely long polynomial centered at the point A. And the spot where it's centered at is very important, because if it was centered at 0 and you want to do an approximation at 1, you'll get an okay approximation. But if it's centered at 1 and you want an approximation at 12, you're not going to get that great of an approximation. And so that's what that would be. You want to center it at some place where we might want to approximate a value. So this theorem at the bottom says, for a given power series, there are only three possibilities. It converges at the center, which is at A, or it converges for every single value of x, or the more likely case, there is a positive number r, so that the series converges if the absolute value of x minus a is less than r, or diverges if it's greater than r. Notice it is strictly less than or greater than, not equal to on either one. This is going to be used straight from the ratio test that we looked at in 11.6. And the number r over here on the right hand side, the number r is the radius of convergence. If you have a series that converges only at x equals a, then your radius is 0, because you're not going out from that point. Or if it converges everywhere, it would go from negative infinity to infinity. Otherwise, we're going to get an interval like negative 2 to 2 or negative 3 to 3 for a radius of convergence, or an interval of convergence. So, a few examples, like for instance, x to the n, that would just be plugging in 0 and 1 and 2 and 3. You get 1 plus x squared plus x cubed plus x to the fourth, and so on. That has a radius of convergence of 1, and so the interval goes from negative 1 to 1. Whereas the second one, this series, n factorial times x to the n, has a radius of convergence of 0. It only converges at the 0 point, and so its interval is just the number itself. Or if it's been shifted, you have something like x minus 3 when your radius is 1, so you have to go 1 away from 3, so it goes from 2 to 4, not 1 to 1, or negative 1 to 1. Or on the bottom one, this one is a convergent everywhere. So the radius of convergence is infinity, and so those are actually the best ones to do, because if your radius is infinity, then we don't have to check anything. Notice, especially on this third one right here, you'll notice it's bracketed on the 2 but not on the 4. That is not a mistake. When you have a radius of 1 or 2 or 3, something other than the point itself or everything, we have to then test the endpoints to see if it converges at each endpoint. So this this 1, says it will converge when it's on the endpoint at 2, but it does not. It diverges at 4. And so the radius of convergence is 1, but I can include the 2, but not the 4. So let's try one. Find the radius of convergence and the interval of convergence for -1 to the n times x to the n. So the thing we're going to start with on all of these problems is the ratio test, that idea. And so what I want to do is take the limit as n goes to infinity of the absolute value. Now, we talked about in the last section, the -1 to the n, that is going to be going away inside the absolute values because -1, it only alternates between -1 and +1. The absolute value of those would always be 1, so it doesn't really matter. So on the bottom part, I'm just going to use the nx to the n. And on the top part, I'm going to use n plus 1 x to the n plus 1. And when I do that, some of the stuff can simplify a little bit. The x to the n plus 1 minus the part with the x to the n on there. Remember, like bases, you subtract your powers. These two will cancel to give you just an x left over. So I'll have a n plus 1 times x over n. I cannot cancel the n plus 1 with the n. You're kind of stuck there. But as you go to infinity, the n plus 1 over n, that would be the ratio of the coefficients in front. So that would go to 1. Now the x is not changing here because the limit applies to n, so I have to leave the x there. So this is the absolute value of x. I want to make it converge, and to make it converge, this has to be less than 1, because that's what the ratio test says. The ratio test says if it's less than 1, it converges. So now we have an inequality. The absolute value of x is less than 1, which means your x is between -1 and 1. Your 1, since it's just an x by itself, your radius is 1, and so your interval could be -1 to 1. It might include those values. It may not include those values. So for the first part of my answer, for the radius is 1. I know that. But I have to check those endpoints. So to check the endpoints, I have to now plug in those values for the x. These two values have to go back in up there. And so if I do the summation from n equals 1 to infinity, I am plugging in -1 and +1. So I'm going to have -1 to the n times it doesn't matter which one you check first. I'm going to check the +1. So this is the first one, or the number 1. Well, 1 to the n will always just be 1. So I don't need that there. So I'll just get -1 to the n times n. That doesn't look too scary, right? Hopefully not. And so then you have to decide what kind of test that would be. You could do an alternating series test because of the -1 to the n. That would be a possibility. You could also do, say, the test for divergence, if you wanted to. You could do the ratio test if you wanted to. It all depends on what you want to do. If you look at that series and say, what would you do? So, for instance, we just finished the ratio test. Maybe I want to try the ratio test. So if I did the ratio test, I would do the limit as n goes to infinity of, again, the -1 to the n would go away just like it did before. So I just get n, and I get m plus 1, because you have to add 1 to it. This would actually go to 1. So your ratio test would be inconclusive. So I wanted to show you that just to say, sometimes you'll pick a test and it won't tell you anything. So you'll have to pick a different test. Let's try, instead of the ratio test, let's do, say, the test for divergence. So the test for divergence is almost the same thing. I still have to go to a limit as n goes to infinity, but I just do the sequence itself, not dividing one or the other. And so if I put absolute values on it, I can actually figure out the absolute value. If it's absolutely convergent, then it's still convergent. And so this would just be the limit as n goes to infinity of n, which would go to infinity. And so it diverges by the test for divergence. By the test for divergence. And again, that might not be the only series test you could try, but I know I have to have a parenthesis on the right hand side. Then I want to test the other version. What happens if I do the one with the negative 1 on it? Well, you'll notice that it comes out almost identical. The summation from n equals, not infinity, n equals 1 to infinity. That would be negative 1 to the n, negative 1 to the n. Now here I have like bases, the negative 1 to the n, so I could put those together. If you have like bases, you can add your powers together. So I get n, and n is 2n. But 2n would be an even number every single time. If you put any number on there from 1 to infinity, any integer, and you double it, you're going to get an even number. So negative 1 to the 2n would be the same thing as negative 1 squared, which is 1, to the n, which is still 1. So this part is just what happens if you do n, which is actually the same thing we did on the other one. If I do that, I don't even need the absolute values here. If I did the limit as n approached infinity of n, this would go to infinity. This also diverges by the same test for divergence. And so I have to put a parenthesis on that side as well. And so I had the radius correct to begin with. I do not converge on negative 1 or positive 1, but I converge anywhere in between for a radius of 1. So hopefully that makes some sense. Let's try another one. This is x to the n over 2n minus 1. So first thing I want to do is do the ratio test to see what would happen if I wanted to see what the radius would be. And so I get the limit as n goes to infinity of, on the bottom, I leave it the way it is, x to the n over 2n minus 1. Above that, I have to add 1 to the n. So I'll have x, that's not going to look like an x right there. I'll have x to the n plus 1 over 2 times n plus 1 minus 1. And I would flip that over and multiply it. So I have x to the n plus 1 over, on the bottom, I'm going to go ahead and multiply the 2 across. So I'll have 2n, and then I'll have plus 2 minus 1, which is plus 1. And flip the denominator, I'll have 2n minus 1 over x to the n. My x's would combine together. This x to the n will make that x to the n plus 1 just an x. So this is going to look kind of like what we just did. I'll have the limit as n goes to infinity of 2n minus 1 over 2n plus 1 times x. As far as the n's go, as you go to infinity, the power on the top and the bottom are the same, so I get the ratio of the numbers in front. And so that will go to 2 over 2, which is 1. So this thing will turn into just the absolute value of 1 times x, or the absolute value of x, which still has to be less than 1. So again, looks like my radius is going to be 1. That says I'm going to go between -1 and 1. My radius is 1. And my interval might be -1 to 1. But again, I have to check the endpoints. So I'm going to start by checking the positive one, just like I did a while ago. If I check the positive one, n equals 1 to infinity. Remember, the 1 goes in for the x, so I'll get 1 to the n over 2n minus 1. Well, 1 to the n is just 1. And so I just get 1 over 2n minus 1. So again, here you can do a comparison test. That would be one option. You could compare it to 1 over 2n, since it's just got a minus sign on the bottom. You could do whichever one. Let's do a comparison. We haven't done a comparison test in a while. So if I compare this, I'll compare it to, how about the 1 of 1 over 2n. The 1 over 2 could come out in front, and I'm left with 1 over n. I know 1 over n, this part right here, that diverges. That's a p-series where p is 1, which with p is 1, and p is less than or equal to 1, so it diverges because it is a p-series. The multiplying by 1/2 doesn't do a whole lot with the diverging part. And so then all I have to do is make sure they are the correct inequality. So if I compare 1 over 2n minus 1 and 1 over 2n, if I were to plug in 1, I'll get 1/2 on the right, and I'll get 1 on the left. So it looks like it goes this direction. Which it kind of makes sense as well, because the denominator on the left is smaller than the denominator on the right. So your overall fraction would be bigger. So I have a series that diverges that is less than the other series, which means it will push that series up. Comparing these two, that means that my series right here, that diverges by comparison. So it is a divergent series. So the right-hand side, I should have a less than on it, or I mean a parenthesis on it. Let's check the other side. If I do the summation from n equals 1 to infinity and plug the -1 in, I'll have -1 to the n over 2n minus 1. Let's try an alternating series test in this case. This is an alternating -1 to the n. Let's do an alternating series test. So I'm going to write it kind of like what we did back then, and did -1 to the n times 1 over 2n minus 1. I need b sub n, which is the 1 over 2n minus 1. That has to always be bigger than 0. And if you're plugging in 1, you'll get 2 times 1, which is 1. Oh, sorry, which is 2. I can't multiply. 2 times 1, which is 2, minus 1, which is 1. I was jumping ahead. And so that'll be positive, and any value above that would also be positive, so that checks out good. I need the numbers as we go down the list to be decreasing. So if you just plug in a few numbers, I'd get 1 over 1, which hopefully is bigger than the next one. If I plug in 2, 2 times 2 is 4, minus 1 is 3. So 1/3 is less than 1. If you do another one, you'll get 1/5, and then you'll get 1/7, and so on. So yeah, they are decreasing. And the third stipulation is that you need the limit as n goes to infinity of 1 over 2n minus 1 to be 0, which it is. The numerator has a bigger power on the end than the denominator has a bigger power on the end than the numerator. And so all three stipulations check out. So this series, this one, converges by the alternating series test. So actually, I need a bracket on the left-hand side. So it converges on the -1, but it does not converge on the +1. So isn't that kind of strange? But a lot of series actually do that sort of thing, so that's not that crazy. Okay, let's try another one. Find the radius of convergence in the interval of convergence for the series x to the n over n factorial. In factorial, you have to do a ratio test here anyway. So we're going to do the limit as n goes to infinity. On the bottom part, I leave it the way it is. Above that, I'll do x to the n plus 1 over n plus 1 factorial. And that's supposed to be a factorial, but apparently I didn't put enough space in between there. There we go. If I flip it over and multiply it, I'll have the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. The x's cancel just like they've done on the last couple problems. X to the n plus 1 leaves you an x left over on top. The factorials can simplify as well. I'll have a n factorial times x on top. On the bottom, n plus 1 factorial is the same thing as n plus 1 times n factorial. Remember, you just work your way down till you get to the other one. Then the n factorials cancel. So I'm left with the limit as n goes to infinity of 1 over n plus 1 times x. Now, as you go to infinity, 1 over n plus 1 actually goes to 0, regardless of what x is. So this is actually 0 times x, which is 0, which is less than 1. In this case, it does not matter what x is, because it comes out to be 0, which is always less than 1. And so here, your radius is infinity. It could be anything it wants to be for the x values. And our interval of convergence has to be -infinity to infinity. And I don't even have to check anything else. These are the best ones to do, because you can't check your endpoints if you don't have endpoints. The interval doesn't end. And so it doesn't matter what x is, it's always going to work. I like this. Okay, let's try one more. This one will not be quite as nice as the last one. So find the radius of convergence and interval of convergence for this series. So starting the same way, let's do the limit as n goes to infinity. On the bottom part, I leave it the way it is. X to the n over n to the 4th, 4 to the n. On the top of that, I'll have x to the n plus 1 over n plus 1 to the 4th times 4 to the n plus 1. And I flip it to multiply it to make it look a little better. I'll have x to the n plus 1 over n plus 1 to the 4th times 4 to the n plus 1 times n to the 4th, 4 to the n, over x to the n. Now some of this stuff does kind of cancel off. The x to the n, just like on all the other ones, this x to the n will cancel with the x to the n plus 1 to leave you just an x. The 4 to the n and the 4 to the n plus 1 will do the same thing. If you subtract your powers, you'll end up with a 4 left on the bottom. So I'm left with a limit as n goes to infinity. On top, I have n to the 4th on the bottom, oh sorry, into the fourth times x. I'll put the x up there as well. And on the bottom, I have 4 times n plus 1 to the fourth. So as I go to infinity, I get the ratio of the numbers in front for the n's. So there's a 1 here and a 1 there. So I'll get 1 times x over 4 times 1 to the fourth. Oh, sorry. You don't actually need the limit there anymore because the integral is gone. So we'll take the limit off. And so I'm left with the 1/4 you could pull out in front if you wanted to, or you could leave it in there. It's 1/4 times x. Or you could do 1/4 times x that way. Either one. But the important thing is you want that to be less than 1 so that it will converge. And so here, to get the x by itself, you would multiply both sides by 4. And so I would say that the x has to be less than 4. The 4 is your radius. That's your r. Since the x is by itself inside the parentheses, or inside of the absolute values, my interval could be -4 to 4. But let's say if it was x minus 1 inside there. So the x minus 1 shifts it over. So instead of -4 to 4, you could be -3 to 5. So you do have to be careful with stuff like that. So with that being the radius, I need to check those endpoints to see if my interval needs to put a bracket on your 4 and -4, or do they stay with parentheses? So let's check the +4 first. So for my +4, remember I'm plugging this in for the x's. So I'll have 4 to the n over n to the fourth, 4 to the n. Ooh, that is nice. I like that because the n to the fourths cancel. Oh, sorry, the 4 to the n's. I said it backwards. The 4 to the n's cancel. And so you get 1 over n to the fourth. This converges with no real testing needed. It's a p-series where p is 4, which is definitely greater than 1. So the 4 needs a bracket on it. So nothing really there to test. Boom, it converges. I'm good. Let's try the other one. Maybe the other one's that easy as well. The summation from n equals 1 to infinity. If I plug in -4, I'll have -4 to the n over n to the fourth times 4 to the n. It's not quite as easy. What I would suggest, or what I see to do here, is the -4 to the n is the same thing as -1 to the n with 4 to the n as well. So I could break that up over n to the fourth, 4 to the n. And then the 4 to the n's cancel, so you just have -1 to the n over n to the fourth. And here you have a couple options. One option is to do the absolute value of it and see if that converges. I know it would because it'd be a p-series, but it's also an alternating series test. So just to be different, to show you that again, I'll do an alternating series test. So if I wrote it as the summation from n equals 1 to infinity of -1 to the n times 1 over n to the fourth. My b sub n would be 1 over n to the fourth, which has to be greater than 0, which it is. There's nothing on the bottom to make it negative, and the top number is always 1, so that's okay. You have to be decreasing, which you are. If you plug in 1, you just get 1. The next one would be 2 to the fourth, which is 16. And then the next one would be 3 to the fourth, which is 81. And so anyway, it is decreasing. And then the limit has to be going to 0, which it does because there are more ends on the bottom than there is on top. So all that checks out. That is good. So yeah, this actually converges. This converges by the alternating series test. And so you need brackets on both sides. And so I have a radius of 4, and it converges on both endpoints, which is kind of cool. And so that's how you do radius of convergence, doing the ratio test, and then you do the interval convergence by plugging those values that you get in for your interval back into your series, and then you may have to use a different test like alternating series, comparison, whatever, to see if it converges at that endpoint. So hopefully that makes sense, and we'll carry this sort of idea straight into the next section about doing power series as functions.